Let me first introduce Dr. Xiaochen Xian. She is currently assistant professor in the H. Milton Stewart School of Industrial and System Engineering at Georgia Tech. So before joining Georgia Tech, she was assistant professor in the Department of Industrial and System Engineering at UL Florida. Her research mainly focuses on big data analytics and system informatics. Specifically, her research includes big data streaming monitoring and sampling, engineering knowledge enhanced complex process modeling and diagnosis, on-demand machine learning and system informatics, and spatial temporal real-time prediction. Dr. Xian's research has been supported by federal and local agencies, including the NSF, NIH, and the Florida Center of Cybersecurity, and the Florida Space Grant Consortium. She is also the recipient for multiple awards, including NIH NIIB Trailblazer Award, Cottmeyer Family Faculty Fellowships, multiple papers award from Informs, IISE, and IEEE, and feature articles in the IISE magazines, AIE, and the Young Stars. Dr. Xian is an associate editor of IEEE Transaction of Automation Science and Engineering. Let's welcome Dr. Xiaochen Xian for her presentation today.
Yeah. Thank you very much, Bo, for the very kind introduction. And thank you for inviting me for the webinar. I'm very honored to present today. And good afternoon and welcome to my presentation to everyone. Today, I'm going to introduce my own experience in research in sleep disorders. I hope everyone can see my screen and hear me. If you see any problems, let me know. Okay, so this is the outline of my presentation today. I will first start by introducing the domain of sleep data analytics. I'll focus on describing what are the problems, the major focuses from experts in this area. And to our QSR committee, you might be interested in the data types and uniqueness of this application. I'll also introduce the major challenges, opportunities in this area. And then I'll highlight a few of my research projects as attempt to apply machine learning to trying to solve some of these challenges, followed by conclusions. All right, so I guess most of our QSR members have had a lot of experiences in AI and data science. As in the sleep disorder domain, in the past few decades, the synergy of AI and data science has demonstrated a lot of success in terms of more accurate diagnosis, personalized treatment strategies, and understanding on enhancing sleep health. So I want to do a quick summary here about the major applications of AI and data science used in sleep disorder. And I'll classify them by clinical task and sleep disorders. So by clinical task, the major applications of AI and data science methods are applied on sleep scoring, diagnosis of sleep disorders, understanding of sleep disorders, and treatment and management of sleep disorders. I'll take sleep scoring as one example. Sleep scoring is one of the most crucial and studied clinical tasks. Traditionally, it has been a manual process of extracting sleep cycle information and identifying associated events from sleep data. For example, sleep staging is a very, very common task for most of the sleep disorders. So basically, we want to recognize from data what sleep stage is the patient in. And there's also other event detection like arousal scoring, try to detect the arousals of the patients, respiratory event scoring, movement scoring, especially for movement-related diseases. From an AI and a data science perspective, these tasks are considered classification problems, trying to identify certain events. And although this procedure is traditionally very complex, time-consuming, and labor-intensive, AI and data science can help process vast amount of data, sleep data rapidly, and automate, streamline this process. It can help minimize the inter-rater variability. So many of the research has been focused on this. I'll talk about some of them later. If we categorize AI and data science applications by sleep disorder, we also have a quick summary introducing some of the major sleep disorders. Sleep disorder is actually surprisingly prevalent, maybe because sleep is such a big portion of our life. So actually, whenever I give a presentation of sleep disorders, there are always some audience come to me and say, "Oh, I experienced some of the symptoms." So this is really helpful to me. So and also doing sleep disorder research has helped myself as well and my family personally. Most studies in the AI area on sleep disorders explore like sleep apnea, insomnia, and narcolepsy. Some of the studies delve into less studied disease like restless leg syndrome, and most other types of sleep disorders still remain highly underexplored. I'll introduce several of the sleep disorders that may be interesting or like popular. So the most prevalent sleep disorder for a very large population is sleep apnea. It is characterized by sleep breathing repeatedly stops and starts during sleep. So that prevents the patients from necessary oxygen intake and causes very poor quality sleep. Existing AI and data science methods have been focusing on how to enhance the accuracy and efficiency of diagnosis and detection by employing various types of machine learning methods and integrating various types of sleep data. It can help guide the treatments by predicting outcomes. And also enhance the endotyping, phenotyping of more specific types of apnea. And also it can help enhance patients' risk stratification and screening. Insomnia is not also another prevalent sleep disorder that can lead to a wide range of symptoms, including difficulty falling asleep, experiencing tiredness at different periods of time, and it's also widely studied in the literature. I'm sure this symptom has bothered most of us from time to time. And using AI and data science studies, we are able to employ various type of machine learning models for prediction, for insomnia prediction, and help us for phenotyping. Restless leg syndrome is one of the disorders that I actually found out I experience from time to time after I started sleep disorder research. It is a sensory motor sleep disorder characterized by an uncontrollable urge to move the legs, especially during sleep. Usually, it's also accompanied by uncomfortable sensations. So this is a chronic condition with significant negative impact on sleep quality and quality of life. Again, AI and data science can help with the diagnosis, treatment, and guiding treatment for this type of disease. Now I want to introduce some common data types used in sleep disorders. Mainly, data used in sleep disorders can be categorized into sensor data and survey data. So because of the advancement of AI and data science together with sensor technology, we have been able to acquire and utilize an increasingly diverse range of data types. Here is a quick summary of common sleep disorders and the corresponding major data types, like for sleep apnea, because it's a respiratory related sleep disorder. The mostly used sensor type of data are like PSG including like oxygen saturation, snoring, respiratory rate and efforts. For like restless leg syndrome, for example, this is mostly movement related disease. Then it's mostly using the body movement information in PSG. So here are a quick introduction of some common sleep data. So PSG, that stands for polysomnography, it involves recording of multiple digital physiological signals like brain activity, eye movement, muscle activity, heart activity, oxygen saturation, respiratory snoring, so on and so forth. So PSG provides the most detailed information on sleep architecture and clinical diagnosis of sleep disorder. It is so far still the gold standard to diagnose various types of sleep disorder. And it's also the primary sleep data type explored in AI and data science. Although there are some efforts trying to move PSG on an at-home setting, most of the PSG recordings remain in lab, so it makes the patients less comfortable to sleep with, and it's hard to challenge, especially it's challenging to apply, especially for young children. This is a common like PSG recording that we see over time. So this is like about like 30 seconds of recordings with multiple channels. This is usually how what physicians look at diagnose sleep disorder. Other than PSG, VSG is also a conventional way for data collection during sleep. It is a non-invasive method because we only need to take the videos. And it's very easy to use. And however, it is time consuming and also raises some concerns like privacy issues. And analysis of VSG is relatively harder. Another type of sleep data is actigraphy, which uses like a wristwatch like a device to continuously monitor movement and rest cycles of a patient. This is an example of recording the patient's movement over 24 hours, 7 days. So you can see like their movements during the day and they're relatively stable overnight. So this method is non-invasive, cost-effective, very ideal for large-scale population. But this method is relatively lower quality because it could be contaminated by a lot of artifacts and noises. CPAP is a pretty specific type of data collection for sleep apnea because it's based on like it's data collected during treatment, but it provides a lot of good information for patients during sleep as well. Other than these conventional techniques, so there's also some emerging sensors like wearable sensors, smartphones, even 3D visual photography have been used for sleep apnea. There has been an increasing trend of integrating this type of emerging sensors in the AI machine learning community. Besides sensor data, there are also a lot of survey data in sleep disorder. So things like sleep diaries, sleep questionnaires, life history, this type of data collected from the patients that patient reports. So these type of data are usually helpful for diseases that are relatively subjective. For example, for some insomnia patients, their sensor data could be perfectly normal. The sensor data would tell us the person has been asleep, but the patient cannot feel so. So the patient feel that they haven't fallen asleep over entire night. So in those cases, survey data will be very important. Following these applications, I want to talk about some well-known challenges that has been identified in sleep disorder. First of all, posed by the inherent complexity of sleep disorders, because sleep disorder is multifaceted, it has diverse manifestations, like over the entire body of the patient. So, and it's also co-occur with other medical conditions, makes it very complex to analyze. Also, the patients are highly heterogeneous, that makes personalization very hard. From the data handling and analysis perspective, sleep data is very heterogeneous, and there have been some quality concerns. The sleep data could be originated from various sources, from various type of devices to record the data. And also data recorded during sleep could be low quality. So it may involve a lot of noise, artifacts, missing values, and others. Sleep data exhibits high temporal dynamics and variability. The data representation integration has been an issue for long. How to effectively use domain knowledge has been an ongoing investigation. So I understand this is a very, very high level summary of this application. So our group have published this book called Handbook of AI and Data Sciences for Sleep Disorders, which has much more detailed information about how like these methods, data, like novel emerging technologies of AI and data science, if you're interested in looking at. All right, so I will now demonstrate a few of my research projects trying to tackle the challenges I mentioned before. So the first paper here is a weakly supervised deep learning approach for a sleep apnea severity detection using coarse grain labels. So we already know what sleep apnea is. It's a very common sleep disorder marked by breathing difficulties during sleep. It could be fatal for young children and infants, and it highly impacts the daily life quality for patients. Most of the patients still remain undiagnosed, and accurate, affordable diagnosis is the key. So to do so, the challenges here is in the procedure of sleep apnea diagnosis. The gold standard of sleep apnea diagnosis is still full night PSG. And the procedure is the patient coming to the lab for the sleep in for one night to record their physiological signals. The physician would look at the signals to manually annotate the recordings to provide diagnosis results that measures the severity of that patient. However, this procedure is labor-intensive, time-consuming, and retrospective, which is falling short for the diagnosis need of a large population. There are already some existing machine learning techniques that try to automate it, but we know that using machine learning methods, it requires massive training data labeled for sufficiently short time intervals to ensure accurate detection. But this is not really available due to high cost of manual labeling. So to this end, I want to introduce the two types of labels that we have and what we want. Coarse grain labels refers to the label information corresponds to a longer time period, longer time interval. And the label information is a binary label. It's either 0 or 1, indicating the apnea absence or presence for that epoch. This is a relatively inexpensive available. We can use some surrogate measures in practice to use it as coarse grain labels. However, physicians sometimes prefers these fine-grained labels to understand the severity level of a patient and help us to subcategorize, phenotype the patients based on their severity. So that's why we need this type of fine-grained labels, which is at an instant level, which is much shorter time interval. And the label inside is a continuous label representing the latent apnea severity for that instance. So you can see it's a much more detailed fine-grained label comparing to the coarse-grained ones. However, obtaining this fine-grained label is very expensive, usually unavailable. So our job here is to automatically learning the fine-grained labels using that with the help of coarse-grained labels. In the literature, most of the machine learning methods would require these fine-grained labels. So if we look at the weakly supervised learning perspective, where we only have coarse-grained labels, the closest branch of research is probably the multiple instance learning. For example, some of the studies try to improve spatial granularity of image segmentation. However, using these coarse-grained labels. However, these type of methods, they are not really designed for physiological signals, so they cannot recognize the conceptual structure of physiological signals, especially with dual granularity over the temporal domain. And also, there is a lack of integrating apnea diagnosis related knowledge into these methods. So to this end, our objective here is to leverage this coarse-grained label data with the incorporation of domain knowledge to establish a weakly supervised deep learning framework to automatically estimate the fine-grained apnea severity at high temporal resolution, so we can quickly and precisely diagnose apnea at a low labeling cost. This is an overview of our proposed framework. So at the data preparation stage, we have this coarse grain label ready. That's our pretty much only labels. And this is our physiological signal segments. And from these segments, we extract some ancillary features regarding clinical knowledge. I'll talk about this a little bit more later. So during the model training stage, we will use this we'll feed this physiological data into our DeepCNN framework. and try to, which is regularized by a novel loss function term that we propose, try to automatically learn this fine-grained labels here. And in this loss function, there are two important terms. One term, we call it a dual granularity consistency loss, which is trying to make sure the coarse-grained labels and the predicted fine-grained labels corresponds to each other. They are not on the same temporal scale, but we try to find a way to confirm their relationship. And the second part of it is the knowledge enhanced ordinal loss, where we incorporate domain knowledge using the ancillary features to help regularize our learning of the predicted labels. Okay, so this is how the dual granularity consistent loss works. The job is to use this loss to ensure we can learn a good deep CNN model to map the physiological signals to the predicted fine-grained labels. On the right-hand side, to do this, on the right-hand side, we are trying to figure out what are the relationships between the fine-grained labels with the coarse-grained labels. We know that high apnea severity would lead to high likelihood of apnea presence. So that means they have a natural, conceptual relationship underneath. So we try to infer from the fine-grained severity based on an aggregation function that we propose. Where from the fine-grained labels, we should be able to infer the coarse-grained labels. So that is the likelihood of the coarse-grained labels from the fine-grained labels. On the left-hand side, we directly infer the coarse-grained labels from the signals using Y here. So then we have two representations of the coarse-grained labels. One from the signals and one from the predicted fine-grained labels. And the dual granularity consistent loss try to minimize the differences between them so that we have a good mapping from the signals to the fine-grained labels. And the second loss here, we call it a knowledge-enhanced ordinal loss. So this is trying to incorporate clinical knowledge. So for sleep apnea, for example, our physician told us, when they try to diagnose apnea, there are two things important they would look at. One is the flow volume, that is how much airflow the patient take in, and snoring, how much snoring there is. So we use summary measures of the flow signal and snoring signal to come up with these clinical knowledge-driven features that helps with our learning. Say, if the patient has high flow intake, then they have lower probability or lower severity of apnea here. So we try to use these relative magnitude of these features to help regularize our learning. However, this relative order would suffer from noise. Say, we say here this part, like higher snoring here, like this pair of data, we have higher snoring here, and that should, by domain knowledge, corresponds to a higher apnea severity, but they have a reversed order here. So that is perhaps due to signal noise or symptoms complexity. So to deal with this, we propose a novel ordinal alignment function, which is a discrete ordinal class transformation that preserves the ordinal information and is also robust to noises and outliers. And we use this function to penalize misclassification so that when the predicted labels contradicts with clinical knowledge, we would penalize it. Okay, so based on the methods, here is our experiment trying to confirm on the performance of the method. So this is an example recording of the PSG. We selected 4 signals of flow, drive, oxygen saturation, and snoring. And these are the ancillary features we use for 10 epochs, and these are the available coarse-grained labels and fine-grained labels as demonstration. So in our method, this is our training testing data set, coarse-grained and fine-grained labels. So we can see they have very high correspondence. So whenever apnea occurrence is 1, we would observe higher severity. So this is the learning result of how we turn this coarse grain label into a fine grain label, but the fine grain label has much higher granularity. It kind of imputes the latent continuous labels inside this the binary labels. For normal set, we observe overall consistently low severity, and for the apnea data set, we observe some strong like apnea severity during occurrences. We compare our method with 3 different levels of supervised learning and 4 options of ancillary features. Our proposed method with the help of flow and snore performs the best. So our conclusion is first, when we have weekly supervised learning is helpful in many cases if our labels are not as good. We don't have very good labels. And second, the help of clinical features is essential. So if we don't use clinical knowledge-based features, the prediction wouldn't be as good. So our method confirmed that we can achieve a much higher correlation with the reference label and a much lower divergence score with the reference label. Okay, and this is a visualization of the predicted fine-grained labels comparing with the true label. You can see our result, our proposed method has a pretty good consistency of the 2 set of labels, while supervised learning would give us a lot of errors in many cases. Okay. So this is the end of the first paper. So we propose a novel knowledge-enhanced geogranularity consistency loss, trying to automatically find out fine-grained apnea severity using only coarse grain labels integrating domain knowledge. And we validated the results through experiments. The second work is actually built on top of the first work, but it is further integrating Bayesian active learning for query labels to further enhance our estimation. So if we look at the results of the first paper, when we do the predictions, we are doing a pretty good job at the in the normal test data. But when it comes to some high severity cases, we are not doing as good job because apnea data is highly imbalanced. We would have much more like normal observations comparing to apnea occurrences. So that's why we don't have sufficient knowledge to make a prediction. So the second paper is trying to mitigate this by incorporating active learning to let us know when we have insufficient knowledge to make accurate predictions, and we actively query those labels. So the objective here is we try to still work under the steel granularity case, but we integrate Bayesian active learning framework for us to actively query instance level labels at the fine granularity together with the coarse grain labels data for training. So that help enhance the accuracy, reliability, and cost effectiveness of sleep apnea diagnosis. So in the literature, there have been some uncertainty quantification methods, but these methods very few of them touch on the context of weak supervision, and they are also domain agnostic. Using weakly supervised learning approaches, there are some works trying to integrate multi-instance learning with active learning, but there is a lack of instance-level active learning with correspondence uncertainty quantification. So we try to mitigate with this Bayesian active learning framework. So in the training data, we have, again, the physiological signals and coarse-grained labels, the same as our previous setting. And here we use a Bayesian neural network here, trying to learn the fine-grained labels with the help of coarse-grained labels. And the Bayesian neural network would give us also the aleatoric uncertainty, which is the variance of our predicted labels. So these are natural variations of the prediction. We can separate it from the epistemic uncertainty, which is model level uncertainty. This tells us which instance doesn't have sufficient like a model reliability, when we don't have sufficient knowledge to actually make a reliable prediction. And together, we want to incorporate like knowledge misalignment as well based on our ancillary features. Together, design a acquisition function to help us query labels. So we can get some fine-grained labels from the physicians that helps improve the accuracy of our method. So we have like we can enlarge our extend our training data pool and use this to design the novel loss function that considers the label structure of dual granularity between the coarse and fine-grained labels. That is our model training part. So due to the time limit today, I will not go into the details. I'll talk about some high-level insights, like our contribution is in applying this Bayesian neural network, designing novel loss functions with dual granularity and this acquisition function. So the Bayesian neural network is basically help us distinguish between data uncertainty and model uncertainty by using a set of stochastic forward pass parameters that with slight perturbations of the parameters that comes from the same distribution, what are the variations of our prediction? If there are a lot of variations with like a perturbation of a small like parameter settings, then that means like the model is not very reliable. We probably need more specific knowledge to help with the prediction. And with that epistemic uncertainty we learned, we will be able to design this acquisition function which considers both epistemic uncertainty and knowledge misalignment so that we can use this acquisition function to select the instances whose severity estimation has high epistemic uncertainty and also contradicts with clinical knowledge. So we would need like some double checks on those instances to get us more knowledge for estimation. And finally, this loss function we have now, because we can quantify the distributions of the fine-grained labels now, we would use a log likelihood function of the both granularities to help us train the model. All right. So in the experiment, we use pretty much the same setting for apnea detection. So the first thing we confirmed is how does the uncertainty quantification work in our method? So our conclusion here, we can verify that there's indeed a trend of the relationship between our uncertainties with the prediction error and with the true labels. So we can verify from this plot that the instance with high apnea likelihood and high severity may be hard to diagnose, just simply because we have much less data there. And also we checked on our Bayesian neural network model, and we can confirm that applying Bayesian neural network would help us improve the prediction result. And this is under different query budget, what are the estimation performance of sleep apnea severity? We can see with increased budget, we will indeed have lowered the prediction results, the prediction error. And comparing with other benchmark methods, not considering the uncertainty quantification, knowledge misalignment, our methods are the best ones. All right, so this is a quick introduction of the second work where we try to further improve the proposed apnea detection methods under the Weakly-Supervised learning framework. So we can see that integrating a Bayesian neural network is a big help in terms of both clinical knowledge alignment and also estimation accuracy. All right. So the third work here is on a slightly different line of research. So this work tries to do a deep learning framework for artifact-aware sleep apnea detection. So I'll start with the background of this work. So we already know what is apnea and what is the procedure of automated diagnosis of apnea. There's one other challenges in apnea detection, that is the artifact problem. So what is artifact? artifacts are unwanted noises from physiological signals that come from things like motion, sensor issues, or external interferences. There could be physical or physiological or non-physiological artifacts. So here are some examples. So the blue curve here is the actual physiological signals that we want. But like with the sensor on the patient's on the patient's body, when the patient moves, that actually generates additional signals, like for example, electrical signals that would interfere with the measurement, interfere with the sensor. So we would see a lot of fluctuations. That is not actually what we want to measure, but like it is actually the motion of the patient. This is an example of eye blinking artifacts. So when we blink our eyes, that introduce a lot of spikes that represents the electrical signals that generates from those movements of eyes. And these are some MEG type of artifact in the muscles. So when we have artifacts in physiological data, it could highly corrupt our measurements. Like we would see some bad artifacts that could look wrong. And this is like muscle artifacts that mess up everything. So my physician actually told me working with artifact takes half of their time when they look at like the PSG data. So which is actually takes a lot of their time. They are thinking if there's a way to automatically remove those artifacts so that we can do a much better analysis on the data. So the artifacts could significantly mask the clinical events that we really want to detect, say apnea. And it can obscure the true physiological signal, and it affects a lot on machine learning models because if our models are trained on clean data, it will highly underperform on real world data when there are artifacts in it. To deal with artifacts, there are two primary strategies to work around that. So the first one is artifact rejection. That means we want to just disregard those contaminated segments. This is simple, but however, it leads to a substantial loss of potential informative data. So we would be losing like 30% to 50% of the data from time to time. There's also another track of methods that is artifact correction. So we want to correct our data to remove those artifacts from the measurements so we can work with the clean signals. This is a more practical strategy, but very challenging. In the literature, there have been these four categories of methods dealing with artifacts. There are filtering-based methods like adaptive filtering, wavelet-based methods to do wavelet denoising, blind source separation like ICA, and deep learning related methods. So for all of the methods, they either require reference signals or manual tuning of the parameters. All right. So that means like when we do artifact removal, it requires us to know again what are the actual underlying clean signal is. That is actually never available in practice. We can never really effectively avoid collecting those data and collecting artifacts and only work with clean signals. So that makes the training using traditional methods very, very challenging. So the literature gap here is we want to find out a framework that is simultaneously unified and end-to-end, fully unsupervised, robust, and flexible. By end-to-end here, we mean that we want to do artifact removal and apnea diagnosis at the same time in one step. Okay, so with this in mind, here I want to introduce the problem formulation. We assume we're given a multi-channel physiological signal X, and we assume that X can be decomposed into the clean part of the clean component of X, which is smooth and rhythmic. That's the clean physiological data that we want. XA here is the sparse and distorted artifact component of the signal. And our objective here is train a model that can automatically help learn the imputed clean signals and the artifact signals, and also generate the apnea event label to do apnea detection. The key challenge here is this is fundamentally an unsupervised problem because the true XC and XA are never observed during training. So this makes the problem ill-posed and really hard to deal with. This is our solution to this problem. We propose a autoencoder type of framework to do this task. So first we feed in our corrupted data with artifacts into a shared encoder. So this encoder would take in the original data and learn a latent representation, clean one and artifact one. And they would go through their individual clean decoder and artifact decoder to generate the clean signals and artifact-only signals. And the two estimated signals should replicate the input signal. And then we feed this clean decoder into the apnea detector to generate the apnea detection labels. Our learning objective is to minimize a composite loss function that we designed to accurately recover what is the clean and artifact components. All right, so now I'm going to introduce loss functions used in this method. So this loss function involves quite a few terms, and we categorize these terms into three categories. The first term is for signal reconstruction and apnea classification. So we would have a reconstruction signal to make sure that the estimated clean and artifact components to get jointly recovers the original signal. So we enforce the models do not hallucinate. And the apnea detection loss is a simple binary classification loss that we have. And the second category, we call it the physiological inspired losses. For the clean physiological signals, we impose a smooth loss, which enforces the outcomes of the clean decoder to be smooth. And we also design a cycle-aware regularization to make sure the output of the clean decoder is rhythmic. For the artifact component, we use a sparsity loss to make sure this artifact component is sparse. So this actually matches with our observations of the data. Say if we have a clean physiological data, all of them should be smooth and rhythmic. And for artifacts, they are usually sparse. They are not like the majority of the data. All right. So the last part of the losses is disentanglement loss, and this is the hardest part about how do we clearly separate out between clean and artifact components. So in the output space, we impose a correlation loss. Is basically enforcing the output of the clean decoder and artifact decoder to be uncorrelated. So ideally, the clean component and the artifact component shouldn't interfere with each other much. So we use a correlation loss for the output space. And more importantly, we imply losses for the latent space as well. This is also why we are using this encoder-decoder framework, is because the latent space would significantly help us separate between these two components. So the first loss here we use is the artifact-aware clean latent suppression loss, which is trying to suppress our clean features during artifact. And the second loss here is a latent space regularization for feature compactness, where we try to regularize the clean latent space, asking for less variations in the clean signals to enable imputation. So I want to illustrate how these two losses can do this. So this is like the latent space for the clean and the artifact signals. So you can see that by implying these loss functions, our clean signals is relatively stable, does not have a lot of fluctuations. This ensures that the learned signals is rhythmic. mimics like a true physiological signals. And besides, because of the suppression, clean latent suppression loss, we have the clean latent component is especially constant when we have large apnea occurrences. So when that happens, when we have strong belief there are artifacts in the data, we would ask the clean signal to stay constant, so that during that artifact present periods, we ask the clean signals to learn from those other periods without clean signals, trying to impute what is actually inside behind this artifact component. So that's why we can recover this clean signal well. So instead, if we don't include these latent space losses, we would see that in the latent space, the clean and artifact components, they would interfere with each other a lot, so that the separation is not very clear. Then we would see some leakage here in the learned clean signals, that it is still have some artifact component inside. So our method can really enable the imputation when artifact appears, not only just learning when there are artifacts, but also recovers what is not there when there is artifact. We have some theoretical analysis. I wouldn't go into the details, but the theorem is basically guarantees that the first two algorithms gives us guarantee for the optimization of our loss function to converge to a global minimum. We have two other theories. One guarantees that the loss function encourages effective separations of clean and artifact signals, and the theorem 4 ensures that we can effectively impute the true underlying clean signals when there are artifacts involved. In the experiment, we compare our method with state-of-art unsupervised learning methods like ICA, wavelet-based ICA, IC-UNet. So in the synthetic data, we try to generate some clean components, artifact components, and use the summation of them as the corrupted data to feed into our method. So we are mimicking here by different types of artifact here, trying to mimic the eye blinking artifacts, EMG artifacts, spike artifacts. This is the result. We can see that the red signal here is our imputed clean signals, and black is the original input signal. So we can see even if there is like strong artifacts occurrences, we can still impute the signals pretty well. And this is the result of artifacts. Like the red ones are the blue ones are the true artifacts, and the red ones try to replicate them. And also we have this latent space for clean latent space, artifact latent space to really try to do what they're supposed to do, reflects what are the actual like artifacts components inside the space. Because of the disentanglement capability of our method, we can achieve the lowest estimation error, the lowest MSE. All right. We also test our method on real apnea data set, where so this patient has obstructive sleep apnea, and we have labels for those apnea detection in training data set, and we want to see how well it detects apnea in the testing data set. So this is how our method trying to remove the artifacts and impute the clean signals as much as they can here. And this is the apnea detection performance. So our proposed method is actually performing uniformly well across all cases. And I want to point out that if we apply our method in a two-step fashion, which means we do artifact removal and apnea detection separately, it is actually not as good as doing it as end-to-end framework. So that means doing the two jobs at the same time actually has benefit. The downstream apnea estimation classification task would actually help with the artifact removal part. So this is actually a very inspiring result and surprising to us. Overall, so in this work, we develop a novel end-to-end architecture for apnea detection when there are diverse type of artifacts in the data without the need of clean training data. We incorporate domain knowledge with deep learning to successfully encode the physiological priors into the model's loss function. We provided theoretical guarantees of those loss functions to make sure they work well as we wanted. And we demonstrate the state-of-art performances comparing to the benchmarks. All right, this is actually the end of my presentation. I really appreciate your attention, and I'm really passionate about this research area, and I hope I see more and more QSR members that are interested in this area, and hope more and more researchers are working on this area. All right, so if you have any questions, I'll be really happy to take them. Thank you.
Thank you, Xiaochen, for your wonderful talk. And we have time for a few questions. Audience, please unmute yourself if you have any questions. So, Xiaochen, I have two questions. First of all, in the third topic, in the loss function design for the deep learning, there are many terms, many loss in the loss function. So I also have similar situation. In some case, we have to use multiple loss. What's your recommendation or suggestions how to balance different loss? Because so it's kind of tricky to get the weight for different loss so that we have some good results. To have a balanced result in the end. So I want to hear your suggestions or recommendation.
That's a wonderful question. Indeed, one of the challenges of this work. So I agree that since we have so many components to carry out, to each do their job, trying to make sure this one aspect of properties that we want in the learned outcomes. And indeed, we found that the parameters, like say all the lambdas that we have here, plays an important role. So if we set a very wrong lambda, then it becomes a problem. It will mess up with the entire prediction. Yeah. So the strategy we're using now is trying to search for a good range of those lambdas to search for good feasible space that gives us a good outcome. So my observation is that it's not super hard for us because in some sense, we can actually standardize the loss function, each loss function. So it's not very hard to find a feasible region for us to balance among all of these parameters. We can do a few rounds of searches and comparison using training data. So that has
Mhm.
been good. And we are indeed thinking about how to improve this in the future. So there are mainly two directions that we are looking at. So the first one is a robust loss function design. So we noticed that some of the loss functions, say if we talk about a very straightforward one, like a smoothness loss. So
Mhm.
we recognize that using some formats of the smoothness loss would require more tuning. So that's related to a few things. One is how compatible this loss is to the nature of the data. And also, what is the range of the loss? Does it give us like a big variation? Does it have a long tail of the loss function? So all of those gives us different perspectives when we observe the outcomes. Hope that makes sense to you. And
Yeah.
we try to find out a robust representation of the loss that doesn't require a lot of efforts in terms of parameter tuning. That's one aspect we are thinking about. The second is we try to automate this process if possible. So we can, if we look at this, say, if I give you an example, sorry, I'm not sure why, but my computer is being slow right now.
Yeah, we
So
can see it. We can see it. Yeah.
okay, great. So say these are two cases of like learning outcomes. Like we actually don't know what is the clean output, what is the artifact output. We don't know the ground truth, but it's very
Mm-hmm.
easy to our eyes. Like the first one, that this one is good, but this one has a lot of unwanted noise. So this is easy for us to observe, but not really the algorithm doesn't know. So we are
Uh-huh.
trying to think about how to improve this by providing some human observed output to the signal. So we can try a few combinations of the parameters, and we can manually label them, like how we think, how good we think the outputs are. And we can incorporate this as feedbacks to the procedure. Hope that makes sense to you. And
Mm-hmm.
that could be potentially guiding the algorithm to find the good lambdas themselves.
Sounds good. Sounds good. Yeah. And another follow-up question is, since right now the method is unsupervised learning, um, I wonder, um, so how, because we don't know the ground truth of the clean signal, right?
Mhm.
Um, what's the criteria to tell the cleaned signal? I mean, the signal after cleaning, right, can perform well on the task you are interested in. In real data,
That's a very
in
good.
simulation, we of course we have the simulation. We have the ground truth of the clean signal, right? Yeah, but in reality, how can we utilize the tools for our specific task?
That's a very, very good question. Indeed, if we have the synthetic data, of course, we can just verify them. But like that's also one of the reasons in the real data set we cannot really evaluate the artifact removal performance. So the only thing we can do is confirm with the physician. So we will ask them, okay, can you label for us what in your mind is the with the artifact appearance like region of the signals. So, and we will see if that confirms with our results. Yeah, that's one thing we want to do, we have done. And also another thing that helps us with the evaluation is apnea detection. So although apnea
Mm-hmm.
detection is not really the apnea, artifact removal part of the task, but achieving a better result means that we have a good clean part, so that we can achieve a better prediction. So that's on another level verifies that the artifact removal isn't super wrong. Hope that makes
Mm-hmm.
sense.
Yeah, yeah. Yeah, that's great. Sounds good. Yeah.
Thank you.
I will stop my questions. I do have a lot of interest on those topics. Yeah.
Sure, we can
Um,
talk offline as well.
yeah, yeah. Okay. Any other questions? We have one more questions. We can have one more question.
I have a quick question. So, based on some experience yeah, first of all, great presentation. Um, Based on some experience that I had with wearable sensors, for example, with actigraph, with heart rate kind of sensors, we have some missing value kind of challenge there. And that's problematic especially when you are dealing with real-time kind of monitoring. So did you have that problem as well, or no?
Uh, Also good, also great question. So I want to say that in the sleep apnea detection, we did not really do that. Yeah, like in the artifact aware monitoring, it somehow has a similar sense that we don't have the perfect knowledge. We want to figure out when we should impute, right? So it has this spirit in it. For sleep, that's for sleep study. So the data we usually receive from the physicians are the ones that they feel good. Like say they do have this problem that the patient probably have a loose sensor on their skin. So they don't have a good like measurement recording of the patients. So that night of data would be just disregarded. And they will ask the patients to do it one more time, coming another night, let's do it again. So usually this is the type of data we get that are already screened, good data. But indeed there could be some missing data in the signals, indeed. And I also want to mention, besides like this sleep disorder research that I have a huge portion of work on like adaptive sampling of data, which like we have a lot of missing kind of fashion of dealing with the data, and we try to impute the data, understand, try to learn from like partial observations of the data. Maybe we can talk more on that.
Sure. Thank you so much. I appreciate it.
Thank you.
Thank you everyone for your attendance, and also thank our speaker Xiaochen one more time. And I will stop our meeting today, and thank you guys again.